Alright, so this is a follow-up video to the one that I just posted where I said there's a very simple rule in going from PDF to CDF that you can apply when you have these multiple pieces of a PDF. And so what I've done is, if you watched the previous video, I did this example sort of that was very generic, where I said if you have this generic PDF like this thing on the top, then you can apply this kind of basic formula that I've shown on the bottom that should apply to every kind of row of the CDF. And I just wanted to give you an example of what that might look like. So I've copied over that generic PDF, and I've copied over the rules. So the claim is that if I go and I erase this generic PDF and I go put in something here, and then erase these bounds and actually put in real bounds, so maybe we'll just do that I should be able to apply this very simple formula in order to get the CDF that I want down here. Alright, so up top here, let's just say that I have a PDF that is 0 from negative infinity all the way up to 1, and then it is 0.1 from 1 all the way up to we'll say 6, and then it is then we'll say that it is 0.5 from we'll go from 6 all the way to 7, and then we'll add one more, and then it's 0 for everything else. So from 7 and I guess just to be consistent, maybe I'll erase the equality on the upper side. Alright, so I've got this PDF and I want to know what the CDF is, and I want to make sure I get my limits of integration correct. And so in this first row, I am just going to write f of negative infinity plus the integral from negative infinity to x of 0 du, and that is from negative infinity less than or equal to x less than 1. And so from here, I know that this is just equal to 0, and this portion here, if I were to manage to do the integral, would also just be equal to 0. Okay, so then I can go to my this second row here, and in the second row, I will say, okay, I need to do f of 1 plus the integral from 1 to x of 0.1 du. And I guess to make this easier, or maybe easier to see, I could, just because it's equivalent, because this is a continuous, I can actually make the maybe I'll put the equalities on the other side here. So I'm going to say the equalities are that way. And then that way it's pretty clear that if when I talk about f of 1, I'm actually going to take it from sort of the previous row. So here, when I say f of 1, what I'm really asking for is what happened when you took this entire previous row that you did and you set x equal to this upper bound. Well, this entire previous row was just equal to 0. So this portion is just equal to 0. Now this thing right here, that is going to be equal to 0.1 times x minus 1. And that's just from me plugging in 0.1 du. The antiderivative of that is 0.1 u, and then I plug in, I say, well, 0.1 u from x to 1, and then I end up getting this x minus 1 part. And that's from 1 less than x less than or equal to 6. Okay, so in the next portion, this is where this starts getting more interesting. I can say, all right, I want it to be f of 6 plus the integral from 6 to x of 0.5 du, and that again goes from 6 less than x less than or equal to 7. Now f of 6, we have to say, well, what is f of 6? Well, in order to get f of 6, I just plug in 6 to this expression from the previous row. So I could highlight, I have this expression here and this 6 here, and notice that goes on with this 6 here. So I can plug a 6 into that, and I find that now I have to make sure that I still include whatever contribution comes from this this point. So I still have that. If this was a 1, I'd have to add this together, but fortunately this is just a 0. So f of 6, I know from this previous row here. So I know that f of 6 is going to give me a 0.5, because that's 0.1 times 6 minus 1. So 6 minus 1 is 5. 5 times 0.1 is 0.5. 0.5 plus 0, it gives me 0.5. And then I can integrate this thing, and that's going to give me 0.5 from x minus 6. So then in my last row, I say, well, then this is just going to be f of 7 plus the integral from 7 to x of, and so in this case it's 0 du, and that's from 7 is less than x all the way up to infinity. And f of 7, if we look, that's going to, it has to be 0.5 plus 0.5 times 7 minus 6, and this is just equal to 1, so that means that this whole thing is just equal to 1. 0.5 plus 0.5, and then this portion is clearly equal to 0, so then that whole bottom row is equal to 1 as we expected. So I could sort of write this maybe smaller over here. F of x is equal to 0 from negative infinity to 1, and it is equal to 0.1 x minus 1 from 1 to 6, and then it is, I guess I should make that, and then it is equal to 0.5 plus 0.5 x minus 6, so I could simplify that, because 0.5 plus 0.5x minus 6 is just 0.5 plus 0.5x minus 3. So I could do like 0.5x, minus 2.5 or something, but I can just try to write it in a long form here, just so everyone's clear. And that's for, I'm not going to write it right now, but that's for the range. So this range here corresponds to this range over here, and then finally, and then 1 for x greater than 7. And that's my CDF. So see, it's actually pretty easy. I didn't have to throw in a whole lot of integrals. I just kept using the big F from the previous row to give me the constant that I carry on to the next row. So, so this row became the constant for the next row, this row became the constant for the next row, and so on and so forth. And that kind of reflects how a CDF is always kind of monotonically increasing. And so every value on a CDF is going to be some marginal amount that you integrate under plus whatever value it used to be at. And that's kind of the nature of a CDF. All right, so hopefully that will be a little more clear if you're tired of those long strings of integrals.